Welcome to this chemistry lecture series. Today we're going to do section 3.7, which focuses on solutions and concentrations. This is a fairly small section that focuses on looking at concentration and molarity, which we study at the very end of honors chemistry. Now, even though this is a small section and it is something that might look simple enough, it is a very crucial part of working with solutions. Especially for practical exams when we're working with things like titrations or even with the rates lab later on. This is going to be a very crucial part of how we tackle aqueous solutions and the mathematics that go along with them. So please pay attention and make sure you review what we learned last year in honors chemistry. So let's move forward. So concentration. Concentration is a very key part of chemistry, especially in practical work. The concentration of a solution is the amount of solute dissolved in a specific solvent. So to define these two words, because we are going to use them fairly often in this conversation, the solute is the substance which is dissolved in the solvent to form a solution. So a solution consists of two parts: a very large amount of solvent and a solute that is dissolved in it, a smaller amount of it. The solvent is a substance which dissolves the solute to form the solution. So we're going to have more of the solvent, we're going to have more of the solvent than the solute. There's going to be a very large amount of solvent. Let me write that on here. So for the solvent, there's going to be a very large amount of solvent. Because this is going to be what makes up most of our solution. And then there's going to be a small amount of solute. Because the solute is what our solution is of, and then the solvent is what's dissolved in. So for example, aqueous NaCl, which is just table salt. The NaCl is our, let me do actually a different color. So this is in yellow. So NaCl aqueous will be a solution, which is just, NaCl aqueous is just a fancy terminology for salt water. In NaCl aqueous, we have NaCl, the sodium chloride, which is a solute, because we dissolve a small amount of sodium chloride in a large amount of aqueous, meaning water. Water mean the solvent. Again, why? Because we have a very large amount of water and we're solving a relatively small amount of sodium chloride in it to make that salt water solution. We can use general words when we're talking about concentration, because concentration is a measurement of amount, right? How much of that solute do we have in the solvent? We can use very generic words like dilute and concentrated in order to distinguish different solutions. Dilute generally just means a low concentration, not any particular amount, but just a low concentration, a small amount of solute in solvent. And then concentrated means a very high amount of concentration, a very high amount of solute dissolved in the solvent. So concentrations that are concentrated, or solutions that are concentrated, are going to have a large amount of moles of the solute, while concentrations that are dilute have small amount of moles of solute, or small number of moles of solute. So that's what the words dilute versus concentrated mean. Just a large amount versus a small amount in dilute versus a large amount of moles of solute in the concentrated. The issue with the words like dilute and concentrate is that they don't give us any information, right? Other than if there's a small amount or a large amount, they don't give us workable numbers. We can instead use a numerical value in order to show concentration of a solution. There is always going to be some number of moles in a solution, and that's what we're looking for, right? We're looking for an actual number, an actual value. Now, there are a number of different units that we can use for concentration. In chemistry, we use molarity, or moles per cubic decimeter. In biology and environmental sciences, we use things like weights per volume, or parts per million, parts per billion. I'm sure you've heard some of these before. And we might even use percentages of volume divided by volumes. It depends on what the context is. In chemistry, there's even another one called molality that we're not going to use in this class, but that is used in AP chemistry. But I digress. There are a number of different values or units that we can use for concentration. However, there is one that we mainly use in chemistry, which is called molarity. Molarity is what we learned last year, but it's not normally called molarity in the Cambridge program. We use what we call moles per cubic decimeter, which is calculated by using the equation below. So concentration in moles per cubic decimeter, what we called molarity last year, is the number of moles of solute, so the number of moles of the thing that we're dissolving, divided by the volume of the solution in cubic decimeters. Now, what does this mean? Volume of solution in cubic decimeters. What that means is that we're dividing the amount of moles of solute we put in there by the overall volume of the solution. And you have to be careful, because when we dissolve the solute in the solvent, it adds volume to that solvent. Meaning that when we talk about the volume of solution, it is not the same as volume of solvent. This is the volume of the finished solution, not of the solvent. So you have to be careful of adding the solvent after the solute so you can get the right volume. Now, what is this dm to a third power? Remember, the 1 dm to the third is equal to 1 liter. So when we're saying moles per cubic decimeter, we're also saying moles per liter. So let's look at a few of those conversions, because this is where things can get interesting. Let me erase those. So like I said, concentration in moles per cubic decimeter. And so let's start there. Concentration is calculated in chemistry in moles dm to the negative 3. So first let's look at this. dm to the negative 3. That negative 3, if you remember from math, x to the negative 1 is the same as saying 1 over x. Right? So when we look at moles dm to the negative 3, we're essentially saying that concentration is measured in moles divided by dm to the third. Because dm to the negative 3 is 1 over dm to the third. And what that does, that because we're using that negative 3, it allows us to write this in a linear way, in where it fits in a line. And so it's easier to type up during the exam. So during the exam, this is what you're going to see. But realize that this is essentially what it means, right? It means moles divided by cubic decimeters. Or moles of solute divided, and I'm going to put here of solute in small print, divided by dm to the third of solution, not of solvent. Now let's look at what that means, because last year we learned something slightly different. Last year we learned it as molarity. And molarity was, if you remember from last year, molarity is moles divided by liters. Well, that's the same thing here. Moles divided by cubic decimeters is the same as moles per liter. Why? 1 cubic decimeter is equal to 1 liter. So we can replace cubic decimeters for liters, meaning that that mole per cubic decimeter is the same as saying moles divided by liters. These all mean the same thing. Moles of solute divided by liters or cubic decimeters of solution. That being said, do not use this on the Cambridge exam. In the Cambridge exam, you must use cubic decimeters instead of liters, and you must use cubic centimeters instead of milliliters, because these are our metric units. So make sure that you're using moles per cubic decimeter for concentration, all right? Because that's going to be very important. This will not score you any points when it comes to units. So be aware of all of that. Now, how do we go about making a solution? Because That's going to be the main thing. Why is it per cubic decimeters of solution? What does that mean? Well, if I have, let's say, 1,000 milliliters of solvent, and then I add 100 grams of solute to it, then we're no longer going to have a solution of 1,000 milliliters, right? If I add 100 grams of whatever solute I'm adding to 1,000 milliliters of solution, the volume ends up being larger than 1,000 milliliters. That solute I'm adding has volume that it's adding to the solution. So how would I go around making an actual solution? So let's say I want to make a solution of, let me find here. So I'm going to bring over my periodic table. And we are going to look at something simple, sodium chloride, again, salt water. So let's say we want to make a solution of sodium chloride. NaCl has a molar mass of sodium, 23, plus chlorine, 35.5. So that's 23 grams per mole plus 35.5 grams per mole. So the molar mass of sodium chloride is 58.5 grams per mole. So let's go back to here. And let's say I want to make a solution with a concentration of 2.5 moles per cubic decimeter. And I want to make, and this is a sodium chloride solution, of course, and I want to make 500 milliliters, or 500 cubic centimeters, is what we say in Cambridge, right? So I want to make this solution. How would I go about doing this? First of all, I want to figure out how many grams of the sodium chloride I will need. And in order to do that, I need to know how many moles of sodium chloride I will need. So again, concentration is equal to moles of solute divided by volume of solution, or cubic decimeters of solution. Which means if I have the concentration and I have my volume, which is 500 cubic centimeters, but remember, this is the same as saying 0.5 cubic decimeters, because 1,000 cubic centimeters, which is the same as a milliliter, is equal to 1 cubic decimeter, which is a liter. So if I have my volume and I have my cubic decimeters, I have my concentration, I can rearrange this equation to say concentration times cubic decimeters is equal to moles. So here we have 2.5 moles per cubic decimeter times 0.5 cubic decimeters is equal, 2.5 times 0.5 is 1.25 cubic decimeter, moles, sorry. So that means that in this solution I need 1.25 moles of sodium chloride. Well, if I know the number of moles, I can figure out the amount, right? Because I have the molar mass. If I have 1.25 moles of NaCl, I can do some very easy stoichiometry here to say if the molar mass of sodium chloride is 58.5 grams per mole, then 58.5 grams of NaCl is 1 mole of NaCl. Meaning if I need 1.5 moles of sodium chloride to make this solution, then 1.25 times 58.5, let me do some quick calculations here. So we have 1.25 times 58.5, that's going to be 73.1 grams of sodium chloride. Ooh, why did that happen? Grams of NaCl. So that's how much sodium chloride I need. I need 73.1 grams of sodium chloride to make 2.5 mole per cubic decimeter solution, and I want 500 milliliters of it. So what does this mean? Remember that concentration is per volume of solution, which means this 500 cubic centimeters is of solution, not of solvent. So how would I go around making this? I will use what is called a volumetric flask. So I will grab, and we will see this in class when we do one of our labs, but for now, I will grab a volumetric flask, which is a flask with a wide base and a very skinny, tall neck. And that flask has a single measurement on it. It has one line on it of its volume. So let's say this is a 500 milliliter or cubic centimeter. Sorry. Now we gotta stick with the metric system. 500 cubic centimeter flask. That means that one line on it, that is 500 cubic centimeters. So if I wanted to make the solution, I wouldn't put 500 cubic centimeters of the solvent and then add the solute to it. What I will do is I will grab this flask, and I'm gonna see if I can draw it better on the second try. I'll grab my flask. Oh no, that is even worse. And I will fill it halfway with my solvent, which in this case, and in most cases, it will be water. And then I would add to this flask my 730 or 73.1 grams of sodium chloride. I would add my solute to it. I will shake it up, make sure everything's dissolved, and then once everything is dissolved, I would then add additional water to fill this flask all the way up to the line, which is 500 milliliters. What this does is that it makes sure that the final volume of our solution is 500 cubic centimeters instead of us having 500 cubic centimeters of solvent and adding more solute to it, which will make the volume then be higher than the 500 cubic centimeters that we wanted. So this is just the general procedure to making a solution. I will again make a different video with the actual practical skills showing you the actual glassware and how to do this process. But in general, this is the just a general procedure of how to make a solution. We always add the solute first to a small amount of the solvent, or at least to half of the solvent we're going to use at the end. Shake it, mix it, and then add the rest of the solvent to make the solution to the volume that we want. All right, so let's get on with the lecture. Oops, take this away. So that's how we use concentration to make solutions. Now, we got to keep in mind a few things, and we went over some of this. Moles and mass can be converted to each other using molar mass. And this is what we just saw when we were talking about making a solution, right? Remember that the molar mass is the mass divided by the moles of a chemical. So we can rearrange that equation to give us this equation, which is that moles of a solution, or of a chemical, are equal to the mass of the chemical divided by its molar mass. If I know how much of a mass I have and I can divide that by the molar mass, I will get the number of moles. That also means I can rearrange this equation and say that mass is equal to moles times molar mass. So that's what we did earlier in that problem, right? With the sodium chloride. I'm going to bring that up again. Right here, what we did is that in order to find the grams of sodium chloride that we needed, we multiplied the molar mass of the sodium chloride by the number of moles that we had calculated from the concentration equation. That's how we can go from the concentration and the volume to moles by using the equation and multiplying the concentration times the volume in cubic decimeters. We convert that to moles, and then we can use the molar mass to multiply times the moles to get the grams that we will need. Because keep in mind, we can measure moles with a scale, but we can measure mass. I can't measure 1.25 moles of sodium chloride, but I can measure 73.1 grams of sodium chloride. So, we can use these equations. Given any of two of the following values, then we can calculate the third value. Moles or mass of a solute, and we put those together because, again, we can convert between moles and mass using the molar mass. Volume of solution, again, either in cubic centimeters or in cubic decimeters, because we can convert between the two. And concentration of the solution. So given volume and concentration, I can figure out the number of moles and therefore the mass, which is what we just did earlier. Given the moles and the volume, I can figure out concentration. Given the mass and the volume, because again, I can convert mass to moles, I can figure out concentration. So concentration is equal to moles over volume. Volume is equal to moles over concentration. These are different equations that we are just transforming. And this is very important, because the point here is not for you to memorize all of these equations, right? The point here is to realize that there are really only two equations that matter here. One is the equation for concentration, or essentially the fact that, where is it? Concentration is equal to moles over volume. And the other one is the equation for mass from moles. Mass is equal to moles times molar mass. Once you know these two equations, the other ones are just rearrangement of those equations. And you need to have the critical thinking skills in order to be able to rearrange those equations and get those other equations from them. Essentially, you need to have Algebra 1 skills, which is very important and might not be something that you thought about before, but you will definitely think about in this chapter, because those Algebra 1 skills are key, and you need to have a good foundation on them in order to do all these higher level problems. So let's go to a problem, and this problem includes using that equation that we just learned, but this problem comes from paper 3, from our practical paper. This is from a titration, which we'll talk about titrations at the end of this chapter, where I'll have a whole video on that procedure. But if we read this problem, calculate the number of moles of potassium permanganate, manganate 7 being potassium permanganate. We'll talk about why manganate 7 is permanganate in a later chapter. But calculate the number of moles of potassium manganate 7 present in the volume of Fa2 calculated in B. Now, Fa2 is how they are going to label chemicals in your practical. We're going to do our first practical soon, but chemicals in the practical are not labeled by their name. They're labeled with codes like Fa1, Fa2, Fa3, and then they'll give you information about that chemical. So what this does is that it limits the amount of information you get from reading the label. Instead, they can control the information they're giving you. So it says calculate the number of moles of potassium manganate 7 present in the volume of Fa2 calculated in B. And I've added here that volume was 20.5 cubic centimeters. Then it tells you what Fa2 is. And this will normally be at the beginning of your practical. I have included it here because of the question needs it. But it tells you Fa2 is 0.0200 mole per cubic decimeter potassium manganate 7, or which is KMnO4. So let's bring this up in a different format so we can use it. So a few key things here about this question. First of all, we have this number right here. It's 0.0200 moles per cubic decimeter. That unit tells us that this is a concentration. This is a concentration of this permanganate. Let me clean that up a little. This is a concentration of this potassium permanganate. Now, something else you'll notice here is that this is potassium permanganate, but they give you the name, but they also give you the formula. A lot of times they will do this in paper 3 because the importance here is not to test your nomenclature, it's just to test where you can do the mathematics. So that's one piece of information we have, 0.02 to 0.00 moles per cubic decimeter, which is our concentration of the permanganate. And then we have calculated volume of 20.5 cubic centimeters, which is the volume of the solution. And notice I'm not putting volume of solvent, it's volume of solution, because this is of the whole potassium permanganate solution. So we have volume, we have concentration, and they're asked us to calculate the number of moles, right? So this should be fairly straightforward. Why? Remember that concentration is equal to the moles of our solute divided by the cubic decimeters of solution. Now, the only tricky part about this part of the question is this right here, the m cubed. Notice that our volume here is given in cubic centimeters, so we need to do that conversion. 20.5 cubic centimeters, if we remember, 1,000 cubic centimeters is equal to 1 cubic decimeter. It's the same conversion that you use for milliliters and liters. It's the same as decimeters and cubic decimeters and cubic centimeters. So 1 milliliter is equal to 1 liter, 1,000 milliliters is equal to 1 liter. 1,000 cubic centimeters is equal to 1 cubic decimeter. They're the same thing because a cubic decimeter is a liter, cubic centimeter is a milliliter. So essentially, 20.5 cubic centimeters is equivalent to 0.0205 cubic decimeters. Because all we're doing is dividing by 1,000, or essentially just moving that decimal place over to the left 3 times. Once we have that, we can then, I'm going to click the wrong thing. Once we have that, we can then add those numbers into our equation. We can grab the volume, put in our equation, grab the concentration, put in our equation. But we need to rearrange the equation because what we want here is the number of moles, not the concentration. The concentration is given to us. So if we rearrange this equation, we get that moles is equal to concentration times cubic decimeters, which means our concentration of 0.0200 moles dm to the negative 3 times volume, which is 0.0205 dm cubed. The dm cubes cancel, and we end up with our moles, which are equal to 0.02 times 0.0205, which in 3 significant figures, because notice this number they gave us has 3 significant figures. This number has 3 significant figures. So in 3 significant figures, the answer here is 0.000410 moles. Or if we put in scientific notation, we just say 4.10 times 10 to the negative 4 moles. And that would be our answer. Again, it's a simple conversion. The equation is not that hard. We have to just grab that conversion, just rearrange it. But we have to be careful with things like the fact that the volume is in cubic centimeters and not in cubic decimeters. We're going to do much harder math like this once we go into the titrations. So here you can see the mark scheme. It just says that the number of moles is simply 0.02 times B over 1,000. You'll always see this written in this format. B is the amount of volume that we calculated, right? 20.5 cubic centimeters, so that was given. And then divided by 1,000. Why divided by 1,000? That's just simply that conversion here from cubic centimeters to cubic decimeters. And then the other step is to multiply that by 0.02. Again, why are we multiplying by 0.02? Because of this step. 0.02 is our concentration. Multiply that by the cubic decimeters to get our answer. But the mark scheme shows it all as one single step. Feel free, if you understand this, to do it all in one step. Remember, in the Cambridge exam, it's not so important as to how you're showing the math, as long as you're showing the math and it makes sense and it's proper, right? Because there are a few different ways of approaching this, either stepwise, meaning in different steps like we did earlier, or all in one go like it is here. And to show it in all one go, all you have to do is 0.02 times 20.5 divided by 1,000, and it will give you the same answer. Now notice that the units are already in here in the question, so we don't need to worry about putting units in our answer. So that is a simple way of showing them. All right, it's just the number 4.10 times 10 to the 84, and that's it. That's it for section 7, 3.7. I'll see you in the next video to discuss the last section of content for chapter 3, which is 3.8.